So y'all, when we were here on Wednesday, we did 3-1, and we did most of 3.2. And so the last thing we had done was we found the derivative of this particular function here. So I'm just going to kind of do a little quick recap so that we remember what it was we did. Excuse me. So our function was f of x is equal to x squared minus 2x. And we found the derivative f prime of x to be equal to 2x minus 2. Okay? So let me just kind of zoom in here so we can see that. So we had done the derivative, okay? And again, that was our original function, and this here was the derivative, okay? And so again, remember we talked about, y'all, the derivative is giving me the equation of the tangent line, or the equation of the slope of the tangent line at a particular point, okay? So again, for instance, if we wanted to figure out what is the slope of the tangent line to f of x equals x squared minus 2x at, say, x equals 3, what we could do now is we could come back to this function, right? It's a derivative, but it's still a function. It's f prime of x, and we could plug in 3, and we would find the slope of the tangent line when x is equal to 3. Does that make sense? Okay, so that's what we were doing on Wednesday last week, okay? So I'm going to kind of zoom in here a little bit. I'm going to kind of skip over this one, but here we go. So let me show you something, y'all. What we're talking about right here is how to graph the derivative and how to graph the original function and kind of show the relation between the two, okay? So you can see from here, y'all, that the blue is the actual function itself. It's the f of x equals x squared minus 2x. And then kind of this yellow or orangey one is my derivative, right? So remember what we said. The derivative is giving me the slope of the line tangent to my original function at particular values, okay? So look, I'm going to show you all something here. If I were to say pick, this point right here, y'all, looks like it's like negative a half, right? So if I were to go up right here and I say, look, I want to draw the line tangent to the f of x equals x squared minus 2x when x is negative 1/2. If I were to draw the tangent line, it would look something like that, right? Now, let me ask you a question. That red line, I know it's a little squiggly, but that red line, would the slope of that line be positive or negative? It'd be negative, right? Now, I want to show you something. When I come right here at negative 1/2, look at the value that we have. We have a negative value, right? Because it's giving me the slope. And that's why my y value right here just looks like it's about -3, right? So what that's telling me is that the slope of the red line at that particular point would be down 3 and over 1. Does that make sense? And that's why it's negative there, okay? Now, I'm going to ask you another question. Let me get rid of that red line that we had. We're going to draw another red line. We're going to find the slope of the line tangent when x is equal to 1. So if you notice, if I draw this line here, y'all, what would you say the slope of that line would be? It would be 0. Hey, I want you to notice something. Look at the y value of my derivative when x is equal to 1. The y value right there, since that's an x-intercept, that happens to be 0. Does that make sense? John, am I doing okay? Okay. Okay, so you're cool how the slope of this line here is 0, right? Okay. So remember, that's happening when x is equal to what number? Okay. So since the slope is 0 there, this equation here, this graph right here, is giving me the value of the slopes at that particular point. We said the slope at x equals 1 was 0, didn't we? Isn't the y value right here 0? Does that make more sense? Okay, good. We're gonna do one more, okay? We're gonna do one more. So look, we're gonna pick another. Let me get rid of the red because I don't need it anymore. Okay. Let me do one more point. Let's pick the point x is equal to 2. Okay. We're gonna draw the tangent line at x equals 2. It's going to look something like this, right? Now look at the slope of that at that red line. Would you say the slope of that line is positive or negative?
Positive.
Positive. Now look, when x is equal to 2, isn't the y value a positive number? In this case, it's positive 2. Does that make sense? So what I'm saying here, John, is that the slope of this line, we're going to say it's 2 over 1, right? So we're going to go up 1, 2, and I'm fudging a little bit, but over 1, right? So the slope of this line here is 2 over 1. That 2 over 1 is telling me the y value of that orange line. Is that better? So the orange line is my derivative, right? And remember what the orange line is telling me. The orange line is telling me all the slopes of all the tangent lines of this blue graph at any particular point. Right? So I'm looking for the slopes of the line's tangent to that curve, to that x squared minus 2x at any particular point. That's why when we said, look, when we picked negative 1/2 right here and we drew this line, didn't we say the slope of that line was negative? And that's why my y value of this kind of yellowish line was a negative number. And then when we did it right here at 1, we said, oh, look, the slope of that line is 0. So here's my y value. It's at 0. And then when we did it again at 2, we said, oh, look, it's positive. So we said, oh, my slope of my line there is positive. And that's giving me the graph of my derivative. Okay? All right. So I know it's a little bit messy, guys. We're going to see if we can figure out what's happening. I want to show y'all something real quick. I'm going to kind of look at this part right here. Okay, so look what it says. The derivative of f prime of x is less than 0, which means this here is negative where the function f of x is decreasing. Okay, so let's talk about what does it mean for it to be decreasing and all that kind of good stuff. In case you forgot from college algebra, it's possible. In case you forgot. So, yo, here's my graph, right? Here's my original function. How do I know if it's decreasing? I'm always going to read my graph, y'all, from the left to the right, okay? Look at my y values. Are my y values going up or down? They're going down. Because my y values are all going down here, that means my original function is decreasing. Since my original function is decreasing, my y values on my slope are all going to be negative. Okay, so if you notice, all the y values here of this yellow line are all negative. Now, when we pass that point and we start following our graph again, are our y values going up or down? Is my function increasing or decreasing? Increasing. And that's why my y values from this point are positive. Okay, and then you say, well, what happens right here? Since my tangent line right there, y'all, since my function is not increasing or decreasing at that particular point, that's why we have a y value of 0 right there. Does that make more sense? A little bit? All right, so I'm going to do 2 more problems here, y'all, out of 3.2. And one of them I copied and pasted directly from your homework, okay? All right. So let's take a look here. Let's see if we can find. We're gonna try to graph the derivative of this function f of x. Now notice, y'all, I don't have an equation for my function. I just know that I have a graph, right? But I want to see if I can find the derivative. So first thing I'm going to do, I'm going to find the 2 points where the tangent line is going to be horizontal. Okay. So the tangent line is going to be horizontal right there. So if the tangent line is horizontal, what are the values of m right here? They're 0, okay? So look, y'all, I'm going to do this in green. I'm going to put right there and right here, okay? All right. So now, if I start drawing my tangent lines. Look, there's one of them. Here's another one. That's a little bit more of a secret. Let me clean that up a little bit, make a better one. Okay, here's another one. Look, I'm going to ask you a question. So if you look at this first one here, that's pretty steep. This one is pretty steep too. Kind of looks a little bit the same. Let me try this one here. Does this one here look more steep or less steep than, say, that one right there? It looks less steep, doesn't it? And if I keep doing that, y'all, if I keep coming in closer and closer and closer, they're going to be coming less steep, right? But do you agree with me that they're all positive? Okay. So look what's happening. They're going more steep, more steep, more steep, and then what happens? They become less steep. So they're still positive, they're just smaller positive numbers. Does that make sense? Okay. Now, before I go on, are we cool on how I got that middle piece? I want to make sure that we're good how I got the middle piece before I do anything else. Are we okay on how I got that green curve? If we're not, please tell me, guys. I want to make sure we're good. Anybody not understand how I got that middle piece in the middle? Let's see. I'm going to check. Those of you who are watching online, who's watching online? Noel and Uriel, are we good on how I got this middle piece right here, you guys? Let's see. Let me come back. Okay, good. Just checking with you guys. All right. Let me clean up some mess because there is a little bit of mess. And let's see if we can't figure the rest of it out. Okay. Now, let me ask you another question. We're going to take a look at what's happening on this part of the graph. Okay. Look, y'all, I'm going to start drawing my tangent lines again. If I pick a point right here and I draw a tangent line, would you say the slope of that line is positive or negative? Negative, right? Now, if I pick a point a little further and I draw that tangent line, would you say that one is positive or negative? Negative as well, right? Which one is more steep? Say, let's call this one line 1, and let's call that one line 2. Which one is more steep? Line 2, right? So what does that tell me? That's telling me that my graph is still going down, and it's going down even further because this value is smaller or less negative, I should say, than the other one, right? Since this one is more steep, I'm going to show you what we mean by that. Let's say this one here, let's call this one M1. I don't know, let's say it's something like -2/1, where M2 would be something like -7/1, right? So this is more steep. That's why it's going down even further, okay? All right, so now we know what the right side of the graph looks like. Let's take a look at the left side of the graph. What's happening when we're picking numbers smaller than -2, okay? So we're going to do the same thing here. We're looking at the original function, right? Here's the original function. Guys, remember, question. This graph right here, are those values, is the function increasing or decreasing? Decreasing. So what does that tell me? That those values are also negative. And they're becoming less negative as we approach that point right there, right? Because again, if I draw a line tangent here, it looks like that. If I draw a line tangent here, it looks something like that, right? So they're still negative, but they're becoming less negative. The slopes are getting closer and closer to 0, and that's why from here, my slopes are getting closer and closer to that value of 0 right there, right? John, am I doing okay with you, John? Am I losing you? Okay. So, guys, I want to show you exactly what I mean. And I directly copied and pasted. This is not in your notes, but I just took it directly from the homework. So I literally copy and pasted the last problem out of 3.2? I literally copied and pasted the problem directly out of your homework from 3.2. Okay. Now, guys, I want to point something out. I'm sure y'all are aware now that as you're going through your homework problems, if you get it wrong, you get another shot, right? Does it give you the same problem? No, it doesn't, but it gives you something similar, right? So you may have this exact problem in your homework, or yours may look slightly different. But I'm going to show you the process on how I'm going to figure this out. Okay, when would the tangent line to this curve that I have right here, when would it be equal to 0? Anybody know? At, at x equals 1, right? So at x equals 1 right here, we could draw our tangent line and it would be equal to 0. Everybody agree? Okay, so the first thing I'm going to do, y'all, I'm going to draw my derivative. There's my 0, right? When x equals 1, the y value is 0, right? Because we know this from basic algebra, the coordinates at that point are 1 and 0. Okay, so now, second thing we're going to do, we're going to find what I call a pretty point on my graph. Like, oh, I don't know. Let's try 1, okay? And what I'm going to do here, y'all, I'm going to try to draw a really, really nice tangent line. Something maybe a little bit like that. Let me see if I can make this a little bit better. Not as pretty as I wanted it to be. There we go. That looks a little bit better. Okay. So again, I'm doing this freehand, right? Okay. Let me ask you a question. Do you think we could find, just by looking at what I drew, now again, I know I drew this freehand, but do you think we could find the slope of that line, of that red line? Okay, what would you say the slope, if you were to guess, what would you say the slope would be? Let's see, down 1, over 1, maybe not, down 1 over 2, maybe not. Let's see, down, well, it looks like it could be down 1 over 1, right? Down 1 over 1. Does it look a little bit like that? Down 1 over 1? Okay. So would y'all agree with me that the slope would be -1? Okay, so then what I'm going to do here, y'all, I'm going to put that point right there. Because if the slope is -1 here, that's telling me that's going to be my y value at this particular point. It just happened, the x number happened to be -1 too, but that's not really the important part. The important part was the slope at that value was down 1 and over 1. You see what I'm saying? So like if I were to do another one, let me see if I can do another one. Let me see if I can find a real pretty one. Let's see, let's try this. Let me clean up this mess. We'll do one more. Let's go green. Let's pick 3, okay? If I were to find the slope at 3, okay, let's see. Would y'all agree the slope looks like it'd be 1 there? Right? Okay, so now, what I'm really trying to do, y'all, look at the 3 points that we have. We have this red point, we have this blue point, and we have this green point. Could we draw the line that goes through those 3 points now? Boom. Boom. And there's my derivative. And all we have to do is just plot a 2 points. Okay? So again, when I'm doing this, y'all, the first point I'm always going to look for is when is the derivative going to be equal to 0? That's going to help me find that first point. Okay? So y'all, just to give you a heads up on your homework for this is like the last question or the third question, I think, on the homework out of 3.2. In y'all's case, it's going to be a line. Okay, so how many points do you really need to determine a line? 2, right? So you only really got to do 2. We did 3 just to verify, but you really only got to do 2. And once you do your 2 points, it should work out. Now, guys, one thing I do want to mention is when you're doing your homework for 3.2, this is question number 3, right? So this is number 3 out of 3.2. If you're trying to do yours and you're getting stuck, do me a favor. Take a screenshot of your picture, send it to me on Pronto. I'll make a video. I'll send it out. So again, everybody can see it, right? I want to make sure that you guys are feeling okay about this. And it might take a couple of times to kind of get the idea. Okay, it might take a couple of times. So if you're trying it and you're not figuring it out, take a picture of it, send it to me on Pronto. I'll make a video. I'll send it to the whole class, right? So everybody can kind of see. And then if yours looks similar or different, then you can kind of figure out how to do it. All right. So that was the last part, y'all, of 3.2. What we're going to do today is we're going to go through 3.3. We're just going to do this one section. I mean, we had to finish up 3.2, but we're just going to do 3.3 today, y'all. And you know what? I'm sorry I didn't even talk about what we're doing this week. So let me come back over here. Let me click on this. Okay, so we're in week 4, aren't we? Oh, guys, by the way, quiz 2, what does it do? Wednesday night. Wednesday, right? Okay, so guys, if you haven't done quiz 2, make sure that you do quiz 2. It's due by Wednesday night. It's not due till right before midnight. And I'll remind you guys again on Wednesday. But if you haven't done quiz, or not quiz 2, but quiz on chapter 2, make sure that you do get it done. Okay, so let's see. So what are we doing this week? Let's see. The notes for 3.3 and 3.4 right here, y'all. Again, guys, I'm not actually bringing in physical copies of the notes. So if you want to have them, I'm making this, like this folder was available, I don't know, a couple of days ago. If you want to have like an actual paper copy, make sure that you just go to the library so and print them out. Or, for instance, John was in my pre-cal class last semester. John uploads them to his iPad and uses like Notability. If you want that kind of stuff, you're more than welcome to use it. I'm just not bringing in paper copies. But again, you can access them, guys. You can put them on your iPad, or if you got a laptop with touch screen, you can always do that kind of stuff. So let's see. Today, obviously, we already finished 3.2. We're going to go over 3.3. Y'all, the homework for 3.3 is due a week from tonight. Okay. And I think I had extended the deadline for 3.2 to also make it due a week from tonight. On Wednesday, we're going to go over 3.4. We might start 3.5. 3.4 is not too long. And I want to make sure that we're using a good part of our time. I don't want to sit in a semester be like trying to cram stuff in. You know what I mean? And then, guys, I am recording the lecture, so I'll upload it to YouTube by the end of the day. I'll send you guys a message. Okay. So let's see. Again, guys, you can see right here, homework for 3.3 is due by Monday. Homework for 3.4 is due next Wednesday. I might move 3.5 in here as well, and I'll let you know. The other thing I'm doing, guys, I'm in the week, I'm not just putting like the dates, I'm putting the sections we're covering. So in case you're looking for, hey, when did we do this? It'll be easy to find that. You know what I mean? All righty. So differentiation rules. We're going to talk about constant, multiple, and power rules, sum and difference rules to combine derivatives. We're going to talk about the product rule, the quotient rule, the power rules when we have negative exponents. We're also going to do it with fractional exponents. And combining differential rules to find the derivative of a polynomial or rational function. Okay, so I'm going to, we have basic rules here, y'all. I'm going to get to something called the constant rule. So here is the constant rule. It says the derivative of a constant is equal to 0. Okay, so here is our first problem. It says find the derivative of f of x. So we're looking for f prime of x. This is what we call a constant function, right? If you were to think about a constant function, and in this case it's 8, right? So look, I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. Okay. This is what f of x equals 8 looks like. It is a horizontal line, right? Now, if we were to say, hey, let's find the slope of the line tangent to that curve, we would pick a point. The line tangent, y'all, is going to be on the line itself. But what is the slope of that line? What's the slope of 0? And that's why the derivative of a constant is always going to be equal to 0. Okay. So the derivative of a constant, it doesn't matter if it's a positive number, y'all. It doesn't matter if it's negative. It doesn't matter if it's 1/2. It doesn't matter if it's negative 7/8. It doesn't matter if it's 5 or if it's negative 2 or if it's 0 itself. The derivative of a constant is always going to be equal to 0. Okay. So anytime, so if I were to say, hey, g of x is equal to 1/3, and I were to say, what's g prime of x? You would say it's 0, right? You can say, man, throw a bunch of those on the test, Marcus. Those I know how to do, right? Anytime you got a constant, it's always going to be equal to 0. Okay. All right. Now, we're going to figure out how do we take the derivative of something with a power, something like x to the third. Okay, so y'all, last week we talked about this definition. The limit as h approaches 0 of f of x plus h minus f of x all divided by h, right? That's what we call that difference quotient. And remember what the difference quotient is giving me, right? The difference quotient is giving me the slope of the secant line. I'm just going to kind of do this on the side, y'all, just so you kind of get an idea. So I'll come back to what we have there. But if this is what my graph looks like, and this is the value of x, and this is the value of x plus h, and let's see, this value up here at the top, this would be f of x plus h, and this value here would be f of x. So if I wanted to find the slope, I would say I got to take the difference in the y coordinates divided by the difference in the x coordinates. Well, the space between there is h. So that difference quotient, y'all, gives me the slope of the secant line. But if we make this value of h really small and we start moving, if I could take this point and I could think about it like it's on a track, if I could move that point this way, that value of h is getting smaller, right? So then this point is moving along that, and then we're starting to get that tangent line, right? Okay, so that's just kind of like the idea, right? The concept behind it. But again, we call that thing the difference quotient. We're going to apply it to our problem here. Okay? So first thing I want to do, I want to find f of x plus h. Now, y'all, our function is f of x equals x to the third. So what do you think f of x plus h would look like? Anybody know? Aren't I going to plug this in right here, right? And if f of x is equal to x to the third, wouldn't f of x plus h be x plus h to the third? Does that make sense? Okay. Minus f of x, which we already know is x to the third, okay, all divided by h. Okay. All right, we're going to keep going. We're going to take the limit as h goes to 0. Now, y'all, I'm going to have to multiply that whole thing out like this, okay? Now, let me ask you a question. Do you agree that x plus h to the third would be the same thing as x plus h all squared? Let's see, times x plus h, right? Okay. Now, the only reason I'm doing that, right, because I know the power there is a 1 and I add my x1. Okay? Oh, yeah, x cubed. I'm sorry. My bad. Oops. Yes, should have been x cubed. Okay. Thank you. Now, the reason why I'm breaking up this one like this, y'all, is because in algebra, one of the things that we got to do, we often figure out how do I square a polynomial? Like, how do I square a binomial? Okay. And it's just something we do on the regular. So I'm going to ask you a question. Okay. All I did right here, y'all, I just multiplied this part out and I extended it here. I wrote it out as x squared plus 2xh plus h squared. If you want to do it, you can do it on the side, but that's in essence what it is you're doing. Okay. Now, second piece is I still got to multiply these guys together here. Okay. So we're going to do this part together, y'all. We're just going to go really, really slow. So look, I'm still going to write the limit as h approaches 0. So look, let's distribute this x 3 times. So x times x squared, everybody agree, x to the third? What is x times 2xh? Anyone know? Uh-huh. Everybody agree? Okay. Now, what about x times h squared? What is x? There you go. You got it. Okay. So look, y'all, we've already done this x. We don't need to use it anymore. But we still need to distribute the what? The h. Okay. So look, we're going to go h times x squared. What is h times x squared? It would be x squared and an h, right? Okay. Now, what is h times 2xh? 2xh squared. Very good. John, did I lose you? Okay. Last one. What is h times h squared? H cubed. Very good. All of this is all over h. Okay. I'm sorry? We're good? Okay. Y'all, let's see if there's any things we can combine, cancel, whatever it happens to be. What do you think is going to happen to my x to the third? Look, we got this guy right here, and we got this guy right here. What's going to happen to those? Okay, let's get rid of them. Okay, are there any like terms we can combine? Because I see a lot of x squared h, and I also see xh squared. You know what I mean? Which ones can we combine? Can we combine this one here, say, with this one here? Okay, so what's 2xh or 2x squared h plus another x squared h? There you go. Okay, so guys, I'm going to do this over here on the side a little bit. I'm going to write the limit as h goes to 0. We have a 3x squared h. Okay, so we got those. Okay, can we combine this plus xh squared with this plus 2xh squared? Those two that I circled in blue. Okay, would that give us a 3x h squared? Okay, we still have one other piece. What's the other piece? H to the third, right? Okay, all of this is being divided by h. Okay, we're almost done. Okay, now remember what we said, y'all? If we're dividing by h, aren't we dividing every single one of these by h? Right? So if we're dividing the whole thing by h, we can divide every individual portion by h. So if we divide this first one by h, what are we going to end up with? 3x squared. Very good. Plus, if we divide the second one by h, what are we going to end up with? 3xh. Excellent. And if we divide the last one by h, what are we going to end up with? H squared. Good. Okay. Now, guys, all we've done so far, we've just done algebra. Because remember, the calculus part now comes into play where we're going to take the limit, right? As we take the limit, as h approaches 0, don't we, in essence, plug in 0 everywhere we have an h? If we plug in 0 everywhere we have an h, what's going to happen to this piece and what's going to happen to that piece? They're going to disappear. So all we're going to be left with is a 3x squared, right? And there's our derivative. So we found f prime of x to be equal to 3x squared. Okay. Now, don't hate me, guys. This is the long way of doing the problem, right? But again, the whole point of us being able to like do these shortcuts and stuff like that? Why can we do the shortcuts? Because in essence, they're going to work, right? But why do they work? Because we went through the long way to figure out what the derivative was. But I'm now going to show you the shortcut. So here we have the power rule, and you're like, really, you had to go through all that? Well, it's kind of like the hazing. You know what I mean? You kind of have to go through it, right? So take a look. If we have f of x, right? I don't know what other better way to describe it. It's like the hazing. You got to show it, right? But I want you to. I mean, we did it using the definitions, but now put it this way. Now we're going to talk about the power rule. So now we can start using the power rule, right? You may have. Okay, so look, y'all, if f of x equals x to the power n, the way we find the derivative, that exponent comes down to the front. And then my power gets reduced by a value of 1. Okay, so look at the original function we had. The one we just did right now. It was x to the third, right? We're going to use the power rule. We're now going to find f prime of x. So what do? The power comes down to the front. Then we reduce this power by a value of 1. So we're going to subtract 1 from it. So wouldn't we end up with 3x squared? Yep, every single time, right? Okay, so again, why do we go to so that we can kind of see why it works, right? I mean, the whole point is, why does it work? Well, not just because somebody told you it does, right? I don't want y'all to believe me, everything I tell you. I'm not going to lie to you guys, but yeah. But, we can see, okay, now we can use the power rule. So look, take a look at the next problem. Find the derivative of the function f of x equals x to the 10th. Now, do you think we're going to write x plus h to the power 10 minus x? We're not going to go the long way, right? We're going to do the shortcut. Whoa. I got dizzy all of a sudden. Okay, I'm okay. We're going to do the shortcut all of a sudden. We're not going to do the long way, right? We're going to do the shortcut. So, question. What would the derivative look like? Anybody know? 10x to the 9. Boom. Well, what you can do is you can always double check your answers, right? You know what I mean? You can always double check. But like I think some of the problems say like, can you write out the difference quotient? And then that's what you're looking for. You know what I mean? But you can always double check, right? So the problem says, hey, write out the difference quotient. Don't take the limit. Just write out the difference quotient. And then that's what you're going to do, right? All right. Now, there's something called the sum, the difference, and the constant multiple rule. Okay, so let's take a look here. This is the sum rule. The sum rule says if you're taking the derivative of a sum of two functions, all you're doing is you're taking the derivative of the first function, you're taking the derivative of the second function, and you're going to add them together. Okay? So if you're taking the difference of a sum, take the derivative of this piece plus the derivative of that piece. Okay? The difference rule, y'all, works exactly the same thing. If you're taking the derivative of a difference of functions, take the derivative of the first one, take the derivative of the second one. Since you are subtracting, you're going to subtract. Okay? And then something called the constant multiple rule. The constant multiple rule says if you're taking the derivative of a constant times a function, you can take the derivative of the function and then multiply it by the constant once you've taken the derivative. That's all it's telling me right here. Okay? So look, here's a perfect example. We're going to find the derivative of g of x equals 3x squared, and we're going to compare it to the derivative of f of x equals x squared. I'm sorry? What? No, comparisons, take a look at both of them, right? So let me ask you a question. If f of x equals x squared, what would f prime of x look like? 2x. Everybody agree? Okay. Now, I'm going to show you something. Look at our function g of x. Isn't my function g of x equal to 3x squared? Right? Because that's what it has right here. And isn't that really the same thing as 3 times f of x? Because f of x was x squared? Does that make sense? So wouldn't g prime of x, wouldn't that be equal to 3 times f prime of x? Because if g of x is equal to 3 times f of x, then g prime should be 3 times whatever the derivative of f of x was. What did we say the derivative of f of x was? It was 2x. So 3 times 2x is going to give me what? Boom. Okay. That's all the constant rule is telling me, that I can take the derivative of the function and then multiply by whatever constant I have. Okay? But let me ask you a question. Let me do this in a different color. Here we go. Since g of x was equal to 3x squared, right? And we're going to find g prime of x. Remember what we said about the power rule? What do we do with this number? Okay, what number? So I'm going to bring it down to the front. What number did I already have here? A 3. So I'm going to leave that 3 there. Because why? Because it was there. I can't get rid of it. What do we do with our power? Hold on. What do we do with our power before when we're taking our derivative? Subtract by 1. What's 2 times 3x? Same thing, right? But the reason why it works is because we have that constant. You know what I'm saying? So what I'm trying to show you guys here is we have these rules, and they're pretty, like the constant rule is pretty intuitive. Meaning like, yeah, it makes sense, just multiply by it. But why does it work? Because we can do that, right? And we're showing that we can do that with these particular problems. All right, so let me keep going here. Oh, and take a look. Here are the derivatives of those functions. Here are the original functions and their derivatives. Guys, just to give you a heads up again. So look, here's both of these are our original functions. These here are the derivatives. Now, I want you to notice that we're looking at this as in an interval on the x-axis from -½ to about 2, right? Now, if you're looking from, say, this part, let's see, if you guys are looking right here, say from 0 to 2, would you agree with me that both functions are increasing? Both functions are increasing, right? Okay. Which one is increasing faster? Meaning, which one is the more steep? The 3x squared, right? That one is more steep? Okay. Look at the derivative. Isn't this derivative more steep than that one right there too? Right? Trying to make those connections between the original graph and what my derivative is going to look like. Since this function is increasing faster, that's why this line is steeper than this one down here, right? Because it's steeper because this function is increasing at a faster rate, right? That's why that 6x is more steep than the 2x. Okay. All right. So now we're going to do some basic derivative rules. We're going to find the derivative of f of x. Okay. So remember what it is we're looking for. We're looking for f prime of x. Okay, we just talked about this right now. We're going to do it in pieces. If I want to find the derivative of, say, 2x to the 5th, remember, I'm going to bring down what number? What number is going to come down to the front? The 5, right? Now, what number did I already have there? The 2. What are we going to do with our power? Subtract 1. So that becomes a 4? Everybody agree so far? Okay. Second piece. What's going to be the derivative of 7? 0. Remember we said the derivative of any constant is always going to be 0. So if I have a 7, if I got a minus 11, if I have a plus square root of 3, if it's a constant, the derivative is going to be 0. Okay. Let's go ahead and finish it off. 5 times 2, x to the 4, right? And now our derivative is, we're just doing them in pieces. Okay, we're going piece at a time. Right? We're going piece at a time. All right, let's try another one. We're going to do the same thing here. We're going to find the equation of the line tangent to the graph of f of x equals x squared minus 4x plus 6. when x is equal to 1. Okay, so guys, remember the first thing we're going to do here, you want to find the slope of the tangent line at x equals 1. Okay, because if we're going to find the equation line, the first thing we got to do, we got to find the slope. Now, remember how we find the slope? We find the derivative. Okay, so we're going to go through in pieces. Okay, what is the derivative of x squared? What do we do with that 2? Yeah, it's going to become 2. We're going to reduce it by a power of 1. We're going to get a 2x. Okay, perfect. We're going to do the same thing with this piece here, y'all. Okay. Now, let me ask you a question. That part that I just boxed in the red, what is the power of my x there? Good. So look, I have a minus here, y'all, so I'm going to put my minus. I'm going to bring down the 1. What number did we already have there? 4, right? Well, I already have my negative right here. Okay, good. Now, remember what we're going to do. We're going to reduce the power of x by a 1. But if you said we had a 1 and we reduce it by a power of 1, what power would we have now? 0. Question. Anybody know what x to the power of 0 is? It's always going to be equal to 1. Okay. So we're not going to have any more x's. Okay. Last part. What is the derivative of 6? Good. Question, John? At? At x equals 1? Okay, so 2x minus 1 times 4 times 1. Everybody agree minus 4? Okay. Now, we want to find the slope when x is equal to 1. So what we're going to do here, y'all, we're now going to find f prime at 1. So we're going to plug in the number 1 into our derivative. Okay? So 2 times 1 minus 4 is 2 minus 4. Everybody agree negative 2? Okay. So we found the slope of the line tangent when x is equal to 1. We know the slope is a negative 2. Okay? So, y'all, the other day I talked to y'all about this formula right here. Y minus y1 equals m times x minus x1, right? Okay. In order for us to do that, we got to know a couple of things. So let me clean up, that's not what I wanted to do. Let me clean up this mess right here. Okay, first thing we need to know is we need to know the coordinates of our x1 and our y1. Well, we know the x1 is 1, right? Do we know what the y value is yet? No, we got to find the y value. So how are we going to do that? We're going to plug it in. We're going to find f of 1. So let's see, 1 squared minus 4 times 1 plus 6. Can anybody tell me what is 1 squared minus 4 times 1 plus 6? 2, very good. Okay, now we have our x1 and our y1, right? All right, so let's go slow. We're going to go y minus 2 equals m, which we found earlier to be negative 2, x minus the x value, which was 1. Before we go on, are we good on how we got to where we are? Uh-huh. Okay. So it shouldn't be 2, it should be, what number? That's why I'm asking, what's the value, right? So I'm glad he spoke up. It should be 3, right? There we go. Good. Okay, guys, all we got to do now, solve for x. Y minus 3 equals, everybody agree, negative 2x plus 2? And then we're going to add 3 to both sides. And we end up with y equals negative 2x plus 5. So we found the equation of our line tangent to the graph of f of x equals x squared minus 4x plus 1 at x equals 1. Okay, so guys, quick recap before we go on to the next part. What was the first thing we had to do? We had to find the slope, right? So how do we find the slope? We take the derivative. Since it said, can we find the slope at this particular value, then we plug that value in, that gives me the slope at that particular value, right? Then, since we're going to use our point slope form, we have to know both the x and the y coordinate at that point. If it tells us at x equals a particular value, then we got to find the y value by plugging that value into the original function, and then we can use the point slope form. Does that make sense? Okay, just making sure, y'all. All right. So the second part here, y'all, is something called the product rule. Okay. So the product rule means we're multiplying. Okay. So guys, I told y'all when I took my first calculus class, I had this one professor who came in all the time, right? Okay. So actually, I had another calculus class right a semester or so before that. I took a business calculus course. There's one professor who was great. I still can hear his voice when I'm talking about the product rule, and then we're going to talk about the quotient rule. I can still hear his voice in my head when he talks about it. So the way I'm going to show you the way he taught me, because I took that class in 1993, and I can still hear his voice in my head telling me how to do this. Okay, long time ago, right? So look, suppose we have two functions. This is how he wrote them out. Okay. Why capital F and capital S? I don't know why the capital, but you know what the F stands for? The first one. You know what the S stands for? The second one. Okay, so this is how he said it. If I'm going to take the derivative of a product, this is how I'm going to do it. He says, I'm going to take the derivative of the first times the second plus the derivative of the second times the first. I never forgot that. Now, guys, I want to ask you a question. What's the operation I have in the middle? Right here, I'm sorry. Addition. Does it matter which one I put first? No. So if you want to say the derivative of the second times the first plus the derivative of the first times the second, it's all the same thing, okay, because you're adding, right? But look at what we're doing. We're taking the derivative of one and then the original one of the other, plus the derivative of the other one, plus the original of the one that we didn't take the derivative of. Does that make sense? Right? Okay. So I learned it this way. It had worked out really well for me. How long ago was 1993? 29 years ago? 29 years ago. I still remember it, right? That's a long time. Let me ask you a question. Anybody here 29 or older? No. I'll put it this way. I don't even know, but I know this, right? I remember this part. Been a little while. Okay, so take a look here, y'all. It says for j of x equals f of x times g of x. Okay, use the product rule to find j prime at 2. Okay, so this is what we're going to do. We're looking for j prime at 2. Okay, so I'm going to show what we're going to do. Okay, so we're going to say j of x is equal to f of x times s of x. Or you know what? I'll use the functions they got here because they have f and g. So I'll use f and g. Okay, you see what I mean? The original gangster. Okay, so look what we're going to do, y'all. The way we're going to do this, we're going to take the derivative of the first one. So the derivative of that one is going to be f prime. Now, since this is at 2, I'm going to use 2. You know what I mean? Because I'm not using x, I'm using 2. Times the second one, which is g of 2, plus the derivative of the second function, so g prime at 2, times the first one at 2. And all I'm doing, y'all, is I'm just using this little rule right here, right? What did I do? I just replaced, instead of x's, I'm using 2, okay? Now, let's see if we can actually find the value. All right, so I'm going to zoom in here so I can see this a little bit better. Okay, first question. Do we know what f prime at 2 is equal to? What is it? Yes, it is. Okay. Do we know what g of 2 is equal to? Positive 1, right? Good. Plus, do we know what g of prime at 2 is equal to? 6. Very good. What about f of 2? But it's f of 2, though. What's f of 2? There you go. Good. Okay. Good thing, guys. Any little mistakes, let's make those kind of mistakes here in class because then we can catch it, right? When do you want to make them? You don't want to make them when you're doing this stuff at home or in a quiz or in a test, right? Go slow, you'll be okay. All right, so good deal. J prime at 2, negative 4 times 1, negative 4. 6 times 3 is 18. So what's our final answer, y'all? 14, good. J prime at 2 is equal to 14. Okay. All right, good deal. Okay, so guys, all what we're going to do here, basically in 3.3, we are using, again, these rules here, right? We're going to try to go slow. We're going to make speed. We're going to make sure that we can do this and see if we can't figure it out. Okay, so first thing I'm going to do here, y'all, I'm going to write j of x is equal to f of x times s of x. Okay, now we're going to apply our principle here. So it says for j of x is equal to this expression here, find j of x by applying the product rule. Okay, so remember, the way I'm going to find my derivative, y'all, it's the derivative of the first, so f prime of x times the second plus the derivative of the second times the first. Okay. There we go. Okay, so let's go through piece by piece. We're going to take the derivative of the first. So here is the first function. What would you say the derivative of x squared plus 2 is? Remember, we're going to do it in pieces. What's the derivative of x squared? 2 what? What do we got to do with our power? Very good. We got to subtract it by 1, so 2x, right? What's the derivative of the number 2 itself? 0. Okay, so there's the derivative of the first. We're going to multiply that by the second function. So we're going to write this as 3x to the third minus 5x. Okay. Plus the derivative of the second function. So y'all, what we need to know now is what is the derivative of this guy going to look like? 9x what? Guess again. 9x what? 9x squared, right? Remember, don't we have to reduce our power by 1? So guys, remember, you bring the exponent down in front, right? But then you always have to reduce your power by 1, okay? Minus, what's the derivative of 5x? Just 5, good. Times the first function. What's the first function? And you are done. Okay, now guys, I want to mention something. In your homework, you should not have to like multiply all that business out there. You know what I mean? You should be able to just leave it as it is. Okay. So nobody's going to ask you like, hey, can you distribute all this business? Don't worry about it. Yeah. I mean, you could. You know what I mean? You could do it. I'm not going to tell you to do it, but you could. You can combine like terms and all that kind of stuff. But we found the derivative, right? Now, let me ask you a question. Suppose, okay, remember the first problem, the one we did a little while ago said, can we find the equation of the line tangent at this particular value? Okay, so suppose we said, let's find the equation of the tangent line at a particular value. Remember, we're trying to find the slope of the tangent line. So we found the derivative. Suppose we wanted to do this, I don't know, at x equals 1. Do you agree with me that now all we would have to do is everywhere we have an x in our derivative, we would just plug in the number 1? And then we would already have the slope, and then we could go back to the original function, plug in the 1 to figure out what the y value would be, and then we can find the equation of the line, right? But do I need to go through all that distributing? No, I don't. Because I could, if I wanted to find, say, j prime at 1, we could just plug in a 1 right here, right? We don't need to distribute everything and then plug in our 1. And to me, it would probably be easier to plug in a 1 from right here. No, what would j prime at 1 give me? Anybody know? Remember, we found the derivative, right? The derivative tells me the what? Anybody know? The derivative tells me the slope, right? So this would be telling me the slope when x is equal to 1, okay? So look, just for kind of like, just to make sure they're like, oh, okay, I now understand what you're doing. I didn't really get it before, now I do. Suppose we were to find it at 1. Do you agree with me that this is what I would do? Right? Okay, now let me ask you a question. What's 2 times 1? 2. What's 1 to the third? 1. 1 times 3? 3. 5 times 1? 5. What's 3 minus 5? Negative 2. Boom, we got that part. Plus, what's 1 squared? 1. What's 1 times 9? 9. What's 9 minus 5? Boom. Okay. What's 1 squared? 1. What's 1 plus 2? Okay. Question. What's 2 times negative 2? Negative 4. What's 4 times 3? 12. Negative 4 and 12 is going to give me 8, right? Okay. So again, what that's telling me, y'all, is that when x is equal to 1, the slope of the tangent line is equal to 8, right? Now, could we find, say, the y value when x is equal to 1? Wouldn't we come back right over here, and everywhere we have the letter x, we would plug in what number again? Okay, let me ask you a question. What's 1 squared? What's 1 plus 2? Okay, there's that number. What's 1 to the third? 1. 1 times 3? 3. 5 times 1? 5. So this would be 3. 3 minus 5 is a, so wouldn't this be a negative 6? Okay. Now, couldn't we do this? And then go from there? Okay. So what does the derivative tell me? The derivative tells me the slope of the tangent line in general, and then if you want to find it at a particular point, then plug in that point. You see what I mean? I wanted to use 1 because 1 is an easy number to plug in. You see what I'm saying? 1 is a real easy breezy cover girl number to plug in, so we could find it simply, right? But that's what the derivative tells me. Okay. So again, y'all, I told you when I took business calculus, that professor in 1993, learned a whole lot. Here is something called the quotient rule. What does a quotient mean we have? It means we have a fraction, okay? So this is how he taught me. He said, look, I know the book uses f of x and g of x. A fraction means we have, a quotient means we have a fraction. In a fraction, we have 2 parts. You know what the T stands for? The top. You know what the B stands for? The bottom. Okay, so how do I find the derivative of a fraction? We take the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom what? Squared. Okay? That's how you're going to find the derivative of a fraction. Okay? A fraction, what I mean by a fraction, a function that has a fraction within it, right? I don't mean like 1/2. I mean like x plus 3 over x squared minus 2x plus 1. Something along those lines, right? You have a big rational expression or rational function. Now, guys, the one thing I do want to emphasize here, when we did the product rule, we had a plus in the middle, and when we said when you add, it doesn't matter which one you add first or which one you add second. Here we have a minus. I can't just switch them around, right? Because 7 minus 5 is 2, but 5 minus 7, negative 2, not exactly the same thing, right? Okay, so this is the rule that I'm going to use, excuse me, when I am finding the derivative of a fraction. The bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom function squared. Okay, let's see if we got something here. Here we go. So let me do this just so I can kind of see a little bit better. And again, y'all, I'm going to apply this rule to this problem right here. So we're going to find k prime of x. I'm going to write a big old fraction. Look at the first part. It says we're going to write down the bottom function. What's the bottom function? 4x plus 3. Excellent. Times the derivative of the top. What is the derivative of 5x squared? 10x. Excellent. Perfect. Minus the top, which is 5x squared, times the derivative of the bottom. What is the derivative of 4x plus 3? 4. Excellent. Good, y'all. Divided by the bottom function being squared. So we're just going to write a 4x plus 3 squared. Now, I might do a little bit of simplifying here. Tell you what, I'm going to leave that 4x plus 3 squared all by its lonesome. But I'll probably do a little bit of simplifying on the top. Let's see. Guys, what is 10x times 4x? 40x squared. Good. What is 10x times 3? 30x. Okay. Minus, what is 5x squared times 4? 20x squared. Okay. Question. Can we simplify anything upstairs? Can we combine any terms? 40 and 20. 40 minus 20 is? There's my derivative. The bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom function squared. Okay. And again, guys, that professor I had, he repeated that all the time. Bottom, the derivative of the bottom, or the bottom times the derivative of the top minus the top times the derivative of the bottom function squared. Why did he use things like the top and the bottom? Because when you think of a fraction, you think of the upstairs and the downstairs, right? Why did he use the first and second? Second, because when you're multiplying, you have two functions, the first and the second. Keep it simple, and it makes more sense, right? So that's what I'm really trying to do with you guys here. I'm really trying to apply, guys, what the experience, the good experiences, bless you, the good experiences that I had, and share those with you, right? I'm trying to do that. You know, trust me, I had other professors that were horrible, and I'm trying not. I'm like, okay, let's forget that ever happened, right? I don't want to pass that habit down to you guys. Uh huh. I'm sorry. Say it again. Well, you could FOIL out the bottom, and you could factor some stuff out of the top. But again, all we did is just combine some like terms. Yeah. Okay. Same thing here, y'all. We're going to apply the same principles. So I'm going to write my formula. So h prime of x is the bottom function times the derivative of the top minus the top times the derivative of the bottom all over the bottom function squared. Okay, so let's do it to it. Let's see if we can apply that principle to our problem. Okay, first thing, what's the bottom function? 4x minus 3. Boom, perfect. What's the derivative of the top function? 3. Excellent. minus the top function. What's the top function? There you go. Times the derivative of the bottom. What's the derivative of 4x minus 3? 4. Excellent. All divided by 4x minus 3 what? Squared. There you go. Boom. Okay, so guys, let's at least clean up the upstairs a little bit, and then we'll take care of, we'll stop there in terms of simplifying this thing. Okay. All right, so let's multiply these parts by 3. 3 times 4x minus 9. Excellent. Okay. Y'all, I'm going to ask you a question. Do you agree with me that I'm going to have to multiply this by 4, and then I'm going to have to distribute my negative? Okay, can I do this? Let me just put that 4 over there, and let's distribute a negative 4. And it's kind of like putting your sock and your shoe on all at one step, right? So what is negative 4 times 3x? Okay, and negative 4 times 1? There you go. And finally, 12 x's are going to cancel out. And minus 9 minus 4 should be a minus what? 13. Very good. Boom. And you got it. You got the derivative. Excellent, excellent, excellent. All right. Okay, so y'all, that power rule applies to not only positive values, also applies to negative values. Okay? We're going to do this, the principle the same exact way. Look, we're going to find the derivative of this. What do we say we do with the exponent? We have to bring it down to the what? Okay, so we're going to find the derivative. We're going to bring down the negative 4. Then we're going to subtract 1 from that power. My question to you, what is negative 4 minus 1? Negative 5. And there's our derivative. Okay. So remember, when you're subtracting from a negative, that means you're going even further in the negative direction, right? So you don't want to put a negative 3, right? Because that would be actually adding 1. You're subtracting 1, right? So you're getting even smaller and smaller. You're going even further in the negative direction, right? So actually, from your perspective, it would be this way, right? If you had negative 4, you subtract 1 more, well, now you're at negative 5. Okay, so now, this one says, using the extended power rule and the constant multiple rule. Okay, so really what we're trying to do here, y'all, is show you there's a couple of ways you can do this problem. So look, if my problem is f of x equals 6 over x squared, let me ask you a question. Can I write that like this? Right? So guys, remember, when you have exponents and they're on the bottom part of your function, you can move that term that has your exponent, you can move it to the top, but what happens is your exponent now changes sign. If they were positive on the bottom and you bring them upstairs, now they become negative, okay? So if we were gonna find, say, our derivative, what do we say we do with this number here? Bring it down. So we have negative 2, now we already had 6, okay? And then what are we supposed to do with this guy? That exponent upstairs? We're going to subtract 1. So we already have negative 2, negative 3, right? And then do you agree with me that that would be negative 12 x to the negative 3? And if you wanted to, you don't have to, but if you wanted to, you could write it like this. And it would mean the same thing. Okay? Do you have to write like that? No, you don't. It's just another way of writing it. Y'all, let me ask you one other question before I go on.
can we apply that rule when we say, let's take the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared? Could we have done that also? Do we have a fraction here? Like our original problem?
Was this part already a fraction?
Yeah. So could we have used that rule, the bottom times the derivative of the top minus, you see what I'm saying? If I didn't want to use the rule, like if I didn't want to rewrite this so that now I had an x to the negative power, we could have done that, right? So let me show you, I just want to show you to see, do we get the same answer? Do we get a different? So look, if we were to use that rule, it says the bottom function, which is x squared, times the derivative of the top. What's the derivative of 6? 0. Very good. Minus the top times the derivative of the bottom. What's the derivative of x squared? 2x. Okay. All divided by the bottom function being squared. So it's x squared squared, right? I didn't mean to get all in sync. But that's what it means. Okay. You agree this piece is going to go away? Okay. What is negative 6 times 2x? 12x. What's x squared squared? X to the fourth? Okay. Will anything on the top reduce with anything on the bottom? Won't this x reduce with one of those? And wouldn't we get negative 12x to the third on the bottom? And isn't that the same thing that we got right there? Okay. All it's saying is that you got options when you're going to do your problem. Do you want to write it so that you have negative exponent? Okay, do it. You're still going to get the same answer. Do you want to do the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom function squared? Okay, do it. You're going to get the same answer, right? It's just telling you, you got two ways of getting the same answer. You got two options on how you want to solve it, right? And that's the whole point. It's giving you options, right? Which one is better? Whichever one feels better to you. If you like using the quotient rule, use it. If you like saying, hey, you know what, let me make this so that my power is now negative and just use the power rule, okay, use that. Which way is better? Whichever way feels better to you. Okay. Okay. So now we're going to combine different differentiation rules. All right. So we're going to do this. We're going to find k prime of x. All right. So, y'all, we're going to look at this piece here. Okay. And I'm going to write it like this: the first and the second. Because in that little piece right there, I do have two parts, don't I? I have the first function and I got a second function. Okay. All right. Or, well, I'll do it like that. Okay, so guys, remember when we're using the product rule, it doesn't matter which one we take the derivative first. We're going to have the derivative of one with the original of the other plus the derivative of the other one with the original of the one we haven't taken the derivative of yet. What do I mean by that? Let's leave the first one alone. Let's leave 3 alone. Let's take the derivative of the second function. If h of x is my function, what would the derivative look like? What do we call it? H what? H prime of x, right? You know what I mean? Like we don't have a specific value, but if we're taking the derivative, we say we're going to take the first one times the derivative of the second. You see what I mean? Yeah, we can just, I'm just breaking it up like into two little pieces, right? Plus, now look, we already took the derivative of the second one, so we got to take the derivative of the first function. What is the derivative of 3? 0 times the second function, which is just h of x, right? Okay, now y'all, I'm going to apply that same principle right here. I'm going to do it again because I have another product. You see what I mean? Okay, so we're going to say, let's leave the first function alone. It's x squared. What do you say the derivative of g of x would look like? G prime of x. Excellent. Plus the derivative of the first one. What's the derivative of x squared? 2x, right? Good. Times the second function, which is just g of x, right?
Okay? Now, can I simplify anything in here at all? I'll give you a hint. I can. There's only one piece. What's the only thing I can simplify? The 0 times h of x, right? So this is going to be 3 times h prime of x plus x squared times g prime of x plus 2x times whatever the function g of x is equal to. The whole point of this problem is just to kind of show me that I don't have to have specific values. I can still apply those principles even when I have a general function h of x and we haven't defined it yet. Or we have a general function g of x and we haven't defined it yet. I can still apply those product rules or those different rules to it. Okay? All right. So now, y'all, we're going to do something called extending the product rule. So the product rule, we've been doing it when we have how many functions? Two, the first and the second, right? How many functions do we really have here? We got three. Okay. So I'm going to ask you all to do me a favor. I want you to think of, I'm going to make this up. Q of x, I'm going to say is g of x and h of x. Okay, I'm just kind of introducing a new function. Okay, I'm not doing anything yet. So I'm going to say that k of x is equal to f of x times q of x. Or I'll tell you what, I'll make it even easier. Let's use the letter S for the first and the second. Okay, all I'm saying though is the second is that part right there. I'm thinking of that, those two combined as my second. Okay. Now, remember what we said when we're taking the derivative of a product? We say we're going to take the derivative of the first times the second plus the derivative of the second times the first. Isn't that what the rule was? Right? Okay. Now, I'm going to show you something here, y'all. I'm going to leave that f prime of x alone. Okay. What did we say that s was equal to? Okay, so right here I'm going to put gx and hx. Okay. Now, I'm going to ask you another question. I need to find the derivative of s of x. Okay. So if my second function is g of x and h of x, and we're going to find the derivative of this, don't we take the derivative of the first one times the second one plus the derivative of the second one times the first one? You see what I'm doing here? Are we good so far? Are y'all sure? Matthias, am I doing okay? Yeah? Okay. Jennifer, am I doing okay? Did I lose you? Okay, are you okay? Remember, so right here, I'm saying, look, oh, I have to take the derivative of s, right? So this is my s. How do I do it? I take the derivative of the first one times the second plus the derivative of the second one times the first. So that's what I wrote right here. Okay, so right here, this piece, y'all, I'm going to copy it right over here. I'm going to put g prime of x times h of x plus h prime of x times g of x. Okay, and that on the outside, I still have that f of x out there, don't I? Okay, one last step, y'all. I'm going to distribute this f times each of those pieces. Okay. So, y'all, the way I'm going to write these, I'm going to go in alphabetical order. What letter comes first? F, G, or H? F, right? Okay. So f of x, we all going A, B, C, D, E. We are going like that? Okay. G prime of x and h of x, and then f of x, I'm still going to go in alphabetical order, g of x and h prime of x. Okay. Now, again, this problem here, y'all, was kind of like a long process to kind of show you something here. Okay. Now, remember what we said, when we're taking the derivative of two functions that are being multiplied, we said we take the derivative of the first times the second plus the derivative of the second times the first, right? So we took the derivative of one with the original of the other one, then the derivative of the second one plus the original of the first, right? And because it was a plus, it didn't matter which one we put, right? First or second, because we're adding. What I want you to notice is what happens if instead of two functions, we have three functions. Okay. So if my original function k of x, y'all, is equal to f of x, g of x, and h of x, right? And we're going to take the derivative of that function. I want you to notice something. We took the derivative of the first one. Then we left the second two alone. Then we took the derivative of the second one, that's right, and we left the other two alone, right? And then we took the derivative of the third one and we left the other two alone. Does that make sense? So if we had a fourth one, wouldn't we do the same process? You kind of see like the pattern here? That's the whole point of this particular problem, is to show you that, hey, look, if I have three, take the derivative of the first, leave the second two alone. Take the derivative of the second one, leave the first and the third alone. Take the derivative of the third one, leave the first and the second alone. I'm sorry? It takes you long, right? But this is kind of showing you why you can do it, right? Because we knew the rule worked for two. We just showed that the rule would work for three. We could keep doing that. But guys, in math, there's something called math induction. And by proving something by math and induction says, look, if I can show it for a particular value, and then I can show that it works the same thing for three, then I know that that value is going to apply to 4, 5, 6, 7, and so on and so forth, right? Those of you who end up having to take like more advanced math courses, like guys, I don't know, I want to say I'm not certain if you have to do it in Cal 3. I don't think you have to do it in Cal 2. Maybe, I don't know, I don't remember. It's been a long time since I had Cal 2. But you do stuff by math induction, and that's part of math induction, is showing that, hey, if it works for 2, oh wow, look, it works for 3, then I can say, you know what, I'm pretty sure this is going to work for 4, 5, 6, 7, and 8. You know what I mean? But that's what the purpose of this problem was. Well, but remember, not necessarily real numbers, but integers. Because remember, I'm talking about the number of functions. You see what I mean? So I can't have like 2 1/7 of a function. But I can do 2 functions, 3 functions, 4 functions, so on and so forth. So you're doing it for what we call the natural numbers, or the counting numbers. Right? Okay. So again, what I want you to notice here, Jennifer, look at the pattern. So remember, this is my original function, right? I have 3. I have the first, I have the second, and I have the third, right? Okay, so when we took the derivative, look at the first part. Which one did we take the derivative of? Oh, we took the derivative of the first one, right? And then didn't we leave the second two alone? Okay, look at the second part. Didn't we take the derivative of the second one? And we left the first one and the last one alone? And then look at the last part. Didn't we take the derivative of the last part and leave the first two alone? You see what I mean? Does that make more sense? Okay, so really what I'm trying to show you here, Jennifer, I'm glad you asked this, because I want you all to be honest with me, guys. If it's not making sense, I want you to tell me it doesn't make sense, right? But this is what I kind of want to show you. Suppose I said k of x is equal to f, g, h. What comes after h? Anybody know? Aye, there you go. Okay, and now I said, look, let's find k prime of x. Hey, I don't have to go through that whole process anymore, right? What are we going to do? We're going to take the derivative of the first one. We're going to leave the second, the third, and the last one alone. Then we're going to take the derivative of the second one, and we're going to leave the other ones alone. You see what I'm doing now? And then we're going to leave the first and the second one alone. We'll take the derivative of the third one. We'll leave the last one alone. And then we'll leave the first, second, third alone, and then we'll take the derivative of the last guy. That's the point, right? And if we said, okay, what happens if we add 5? Hey, we can just apply it there too. Does that make more sense? Yeah. Yeah. But that's basically what that rule is telling me, is that, hey, you can do this not only for 2 functions, you can do it for 3, you can do it for 4, you can do it for, if you had 11, hopefully you don't have 11, right? You don't. But you could apply that same principle, right? You're like, oh, okay, I see the pattern now. I see how this thing is working. That's kind of the idea. Okay. These are good questions, y'all. Okay, so we're almost done. We got a little bit more. All right, look. There we go. Okay, we're almost at the end, hopefully. Wow, I didn't realize that 3.3 was such a long section. Okay, guys, let me ask you a question. Y'all want like a 10-minute break? Y'all feel like you need a little 10-minute breather? Kind of let the mind break down a little bit? Okay, so look, it's 2:01. I'm gonna stop recording y'all, but then when we come back, I will start recording again. All that means, y'all,